Electricity now. Number 1, part A says state Coulomb's law and give its mathematical expression. I'm gonna give you a few seconds to answer the question and then I'm gonna come back and show you the answer. So Coulomb's law states that the force is directly proportional to the product of the quantity of the charges and is inversely proportional to the distance between the charges squared. Part B is a direct application on the formula in part A. The formula is F is K Q1 Q2 over R squared, where K is the proportionality constant, which is 9 times 10 to the power of 9. I'm gonna give you a minute to answer the question and then I'm gonna come back. So Q1 is minus 3 nanocoulomb, which is minus 3 times 10 to the minus 9 coulomb. Q2 is plus 5 nanocoulomb, which gives you 5 times 10 to the minus 9 coulomb, and the distance between the two charges is 2 centimeter, which is 2 times 10 to the minus 2 meters. Put that in the equation, you'll get 9 times 10 to the 9 multiplied by the absolute value of Q1, which is 3 by 10 to the minus 9. The absolute value of Q2 will give you 5 times 10 to the minus 9 over the distance between them squared, which is 2 times 10 minus 2 squared. All of that will give you 3.375 times 10 to the minus 4. Number 1, part C says define electric field. I'm gonna give you a few seconds to answer the question and then I'm gonna come back. So the electric field is the force F experienced by a test charge Q0 placed in an electric field divided by the quantity of the charge Q0. Number 2, part A says find the magnitude of the electric field at a field 0.4 meters from a point charge Q equals to 2 nanocoulomb. I'm gonna give you a few seconds to answer the question and then I'm gonna come back and show you the answer. So the formula for the magnitude of the electric field is E is equal to K Q over R squared, where K, the proportionality constant, is 9 times 10 to the power of 9. So that is 9 times 10 to the power of 9 times Q, which is 2 times 10 to the minus 9, so minus, over 4 meters squared, and you will get 1.12 Newton per coulomb. Number 2, part B says the electric field caused by certain charge at a distance 2 meters from the charge is 4.5 times 10 to the power of 5 Newton per coulomb away from the charge. What is the charge? So you need to find Q. You have the distance equals 2 centimeter. You have the electric field. The magnitude is 4.5 times 10 to the power of 5 Newton per coulomb. And you also have the proportionality constant K. It's 9 times 10 to the 9. So the formula is E is equal to K Q over R squared. Solving for Q, that will give you Q equals E times R squared over K. Substituting, you'll get 4.5 times 10 to the power of 5 multiplied by 2 times 10 to the minus 2 squared all over k, which is 9 times 10 to the power of 9, and that will give you 2 times 10 to the minus 8 coulombs. Number 3, part A says find the distance from a charge of 16 nanocoulomb where the electric field due to the charge has a magnitude of 4 times 10 to the power of 4 Newton per coulomb. I'm gonna give you a few seconds to answer the question, and then I'm gonna come back and show you the answer. So you have Q, it's equal to 16 nanocoulomb, which is 16 times 10 to the power of minus 9 coulomb. You also have the magnitude of the electric field, it's 4 times 10 to the power of minus 4 Newton per coulomb. You also have K equals 9 times 10 to the power of 9. So the formula is E is equal to K Q over R squared. Solving for R, you will get radical K Q over E. Substituting, you will get 9 times 10 to the power of 9 to 16 times 10 to the minus 9 over 4 times 10 to the power of 4. And the answer will be 6 times 10 to the minus 2 meters. Number 3, part B says a point charge of Q is 6 nanocoulombs is located at the origin. What is the magnitude of the electric field vector at the point coordinates minus 15 centimeter on the x-axis and minus 20 on the y-axis? I'm gonna give you a few seconds to solve it and then come back. So you have two axes, and you have Q located on the origin, and then you have minus 15 on the x-axis and minus 20 on the y-axis in centimeter. They wanted to find the electric field E, which is K into Q over R squared. R squared is radical 0.15 squared with 0.20 squared because of Pythagorean theorem, and you have to convert the centimeter to meter, and then you have all of it squared also. Then you have K, which is 9 times 10 to the 9. You also have Q, which is 6 times 10 to the minus 9 from nanocoulomb to coulomb. And then you have E is equal to this, which is equal to 8.63 times 10 to the minus 2 newtons per coulomb. Number 4 says 3 charges lie along the x-axis as shown in the diagram. Here on the origin you have Q2, you also have Q1, and here you have Q3. The positive charge Q1, which is 4 microcoulombs, it's at x equals 4. And the positive charge Q2 equals 8 microcoulombs is at the origin. A negative charge of Q3 is placed on the x-axis such that the resultant force is 0. What is the x-coordinate of Q3? I'll give you a few seconds to answer the question, and then I'm gonna come back. So they told you the net force of X is equal to 0, which means that F13 minus F23 is equal to 0. So F13 equals F23, which means that K to Q1 Q3 over R squared is equal to K Q2 Q3 over R squared. You can remove K and Q3, which will give you Q1 Q2 over R squared and over R squared. So now we have Q1 over R squared equals to Q2 over R squared. This is R13 and this is R23. So you have 8 times 10 to the power of minus 6 over x squared. It's equal to 4 times 10 to the power of minus 6 over 4 minus x squared. And that will give you 2 is equal to x squared over 16 minus 8x plus x squared. After that you'll get 32 minus 16x plus 2x squared equals to x squared. And then now you have delta, which is b squared minus 4ac, and b is the minus 16 minus 4 to 1 into 32, which will give you 128. Then after you do the x equals minus b plus minus radical delta over 2a, you will get x equals 13.66 or 2.34. This is greater than 4, so it's cancelled, and this is the correct answer.
Let's do number 5. Consider 3-point charges located at the corners of a triangle as shown in the diagram, where Q1 equals Q3 equals 3 microcoulombs, Q2 is negative 8 microcoulombs, and A is equal to 0.12 meters. Part A is asking us find the magnitude of the force F1 of Q1 on Q3. So now Q1 is here and Q3 is here. Since they're both positive, will this be an attractive force or a repulsive force? Obviously repulsive, because like charges repel. So since it's on the it has to act on this line, so on this diagonal, so I'm just going to do this because it's by Q1 on Q3. So this is, let me call this F1 3 or F1. So how do you find the magnitude of the force? You use Coulomb's law. F equals K Q1 Q3 over R squared. R is the distance in meters. Since we know that A and A is 0.12, so obviously the length of this, the hypotenuse, would be A radical 2. So once we substitute, we get 9 times 10 to the power of 9 times Q1 and Q3 are the same, so it's 3 times 10 to the power of minus 6 coulombs, all of it squared because they're the same, and it's A radical 2, so 0.12 radical 2, all of it squared, and you should get as your final answer 2.8 newtons. Let's do part B as well here. Part B is asking us the magnitude of the force F2 of Q2 on Q3. Now look at the charge of Q2. Q2 is negative, Q3 is positive. So obviously it's an attractive force. Let me use the red pen here. So this is F2 on 3, right? So the magnitude of this would again be k q2 q3 over r squared. Now for this question, for any question, the product of the charges always has to be positive because we're looking for the magnitude, right? So again, it's 9 times 10 to the power of 9 times 8 times 10 to the power of minus 6 times 3 times 10 to the power of minus 6. Now over the distance is a this time, so 0.12 squared. And for this, you should get the answer of around 15 newtons. So that's your answers for parts A and B. Let's continue with parts C to E. What do they want in part C? What is the X component of the resultant force on Q3? D says what's the Y component, and E is what's the magnitude of the resultant. So I'll give you a few seconds, all of you can solve. I've given you a quick diagram of what the scenario is right now, and we'll check in a few seconds. Okay, let's check together. First question is, what's the X component? But first, let's look at the diagram here. So F1 signifies the force by Q1 on Q3. F2 represents the force by Q2 on Q3. So again, Q1 and Q3 both are positive. That's why F1 is going away from Q3. Q2 and Q3 Q2 is negative, whereas Q3 is positive. That's why it's an attractive force. That's why it's going towards Q2. So with that in mind, let's define our positives and negatives. So this direction is positive for X and the up direction is positive for Y. Now F2 is fine with the X axis, but F1 we have to resolve it. Now I've given some angle measures. So since it's both A and A are congruent, it's a 90 degree angle. So now since these are congruent, these angles, so this is also 45 degrees. So I know that this is F1 cosine 45, and I know that the vertical one is F1 sine 45, right? So the first question is, what's the X component of resultant force? So obviously the X component would be F1 cosine 45 minus F2. So you would get something like 2 minus 15, giving you minus 13 newtons. Another way to represent this would be minus 13 I newtons, so you would know that it's the X component. Part D now. What's the Y component? There is only one force along the Y axis, that's F1 sine 45. So the Y component is simply F1 sine 45, giving us an angle of a force of around 1.99 newtons, approximately 2 newtons. Again, you can put this as 1.99 J newtons. 1.99 J newtons, just to be like it's positive up. Part E is very easy. What they want is the magnitude, so you have to take square root 13 minus 13 squared plus 1.99 squared. So it's 13 squared plus 1.99 squared, and the magnitude of the resultant is approximately 13.2 newtons. And that's your answers from numbers C to E. Let's do number 7 now. An electron of mass 9.11 times 10 to the power of minus 31 kilograms enters the region of a uniform electric field, as shown in the diagram, with initial velocity equals 2 times 10 to the power of 6 meters per second, and the electric field is 300 newtons per coulomb. The width of the plates is 0.25 meters. Part A says find the acceleration of the electron while in the electric field. So now let's think about, first thing that should come to mind when they're asking us for acceleration is forces. What force is causing the acceleration, right? Well, there are two forces acting on it, right? The electric force, because there's an electric field, and the weight. Now, the reason why I haven't drawn the weight here is because look at the mass. Look how small the mass is. This mass is so small that the weight can be considered to be negligible. So we don't need to use it in our equations. Now, if anyone remembers, the equation, the formula for electric force is equal to Q times E, right? Now since we have the electric force pointing upwards, and since the charge of the electron is obviously negative, then the force has to be downwards. The direction has to be affected. So now if anyone remembers Newton's second law, which means sigma F net equals ma, right? So using these two equations, we have to do Fe equals QE and F net equals ma. We have to equate these two because the electric force is the net force, which gives us QE equals ma, right? Now another thing to keep in mind is this is projectile motion, right? Because it's going down like this. It's not going like, straight down like in free fall, straight vertically down, nor is it going horizontally to the right or to the left. It's going as a curve. So we have acceleration ax like this, and we have acceleration ay. Now as you remembered last year, ax in projectile motion is equal to 0. So technically we're looking for ay, right? So let's just put a little ay here. Now substituting, the charge of an electron, q electron, is a constant, and it's minus 1.6 times 10 to the power of minus 19 coulombs. So now if we substitute, we get minus 1.6 times 10 to the power of minus 19 times 300 equals 9.11 times 10 to the power of minus 31 ay. When we substitute and simplify, we should get ay equals minus 5.3 times 10 to the power of 13 meters per second squared. Now something to help us make it easier on ourselves, we can put a little j here, just to help us realize, okay, it is a vertical force, because if we all remember, x-axis, y-axis, I is here and j is here, right? So this just helps us that it's a vertical force. So we can just put a little j there. And this is the acceleration of the electron. Let's continue with number 7. You guys can do parts B to D. I'll stop for a few seconds. You can pause the videos and then we'll check after a few seconds. Okay, let's start. Part B asks us to find the time it takes the electron to travel through the region of the electric field. So as you can figure out from this question, what they're trying to ask is, how long does it take the electron to cover this distance, the one I've drawn an arrow through? In essence, the length L. So L is given to us as 0.250 meters. And we have the initial velocity v0, which is 2 times 10 to the power of 6 meters per second. Now you must be thinking, oh, we have acceleration, you have to do, UARM equations. Well, that's wrong. Remember, this is a projectile motion. So it has movement in the x direction and in the y direction. For part B, we are interested in the x direction of motion because it has to cover a horizontal distance. And as we remember, ax in projectile motion is 0. So when the acceleration is 0, it's URM. And what is the only equation we've learned in URM? Delta x equals Vt. We have the V, we have the delta x. All we need is the time. So it is T equals L over V0, right? Because L is the distance it has to travel, or the displacement. So 0.25 over 2 times 10 to the power of 6, and the time is equal to 1.25 times 10 to the power of minus 7 seconds. So it only takes a very small amount of time for the electron to travel through the region of the electric field. Let's continue with part C. Part C asks us what's the vertical displacement as it passes through the electric field. So now when we're thinking of a delta y, we have to think of UARM because we have an acceleration. AY exists. So we have to think of UARM equations. The only equation where we have delta y is delta y equals half AY t squared plus V0 sine theta t. Now, when we launched the object, it was here, and we launched it. What was the angle to the horizontal when we launched it? Wasn't it 0? So this all becomes cancelled because, as we all know, sine 0 equals 0. So substituting, we get delta y equals half times minus 5.3 times 10 to the minus 13. 10 to the 13, and the time is 1.25 times 10 to the minus 7, or this is squared. So we should get delta y to equal minus 0.412 meters. So that's the displacement, the vertical displacement the electron experiences while in the electric field. Let's do part D. D asks us what's the velocity when it is outside the electric field. So notice here they're not asking for Vx, they're not asking for Vy, they're asking for total V. So how do you find the V? Well, V is the resultant of this and this. So in effect, the equation we use to find V is the square root of Vx squared plus Vy squared. Vx is very easy to get, it's always constant because there's no acceleration in Ax. So Vx is always 2 times 10 to the power of 6. Vy is the harder one. In UARM, what was the equation we used to get the velocity in terms of acceleration and time? Wasn't it V equals at plus V0? Using that equation, we get Vy equals minus 5.3 times 10 to the power of 13 times the time plus 2 times 10 to the power of 6. Because wasn't that the initial velocity? Wait, no. It's V0 sine theta. And since theta is 0, then V0 sine theta is 0 as well. Now Vy equals minus 6.59 times 10 to the power of 6 meters per second. We have Vx and we have Vy. All we have to do is square root this and square root this, and then we should get the final answer. So what we do is 2 times 10 to the power of 6 squared plus minus 6.59 times 10 to the power of 6 squared. We take the square root of all of that, and what we should get at the final answer is 6.89 times 10 to the power of 6 meters per second. So this is the final velocity of the electron. Let's start number 8, part A. In a thunder cloud, there may be an electric charge of plus 30 coulombs near the top and minus 30 coulombs near the bottom. These charges are separated by approximately 3 kilometers. Find the magnitude of the electric force between them. So I've drawn a basic square here representing the cloud. So you have 30 coulombs near the top and negative 30 coulombs at the bottom, and the distance is 3 kilometers. So I'm trying to find the force between them. So obviously when you have two charges and you want to find the electric force, you apply Coulomb's law, which says F equals K Q1 Q2 over R squared. Now one thing that you guys should know is that Q1 times Q2 is always absolute value. So if you have a positive times a negative, doesn't matter, the product should always be positive. So the force has to be it has to be positive in short. So K is 9 times 10 to the power of 9. That's a constant, you should know that. Q1 is 30 and Q2 is 30 as well, because the product has to be negative. And since it's in kilometers, you have to make it into meters. So 3 times 10 to the power of 3, all of it squared, and you should get as the final answer 9.00 times 10 to the power of 5 newtons, because they're asking for a force. Let's continue with part B. Part B is asking us what is the magnitude and direction of the electric field that will balance the weight of 3 protons of mass 1.67 times 10 to the power of minus 27 kilograms each. Okay, so I've drawn a little line here. Let's assume we have 3 protons here, proton 1, 2 and 3. I've combined all the weight forces into one weight, which is 3 mg, because their masses are the same, right? So now we have to think, where does the field go? Let's think about the direction first, then we can get the magnitude easily. Well, first we shouldn't find the field. First we have to find the electric force, and from the force we can get the field, right? So now obviously if this is a free body diagram, the force has to be up, right? So let's call this F electric. It has to go up to balance the weight, right? So let's substitute in the equation. We should get the force electric has to equal the force by gravity, or the weight, right? Again, substituting, the force electric has to equal 3 mg. Now what is the force electric? Well, we should know by now the equation of the force is F equals QE, where Q is the charge and E is the electric field. So that's where we get the E from. So that's why I was saying we shouldn't look for E immediately. Let's find the force first, then we can find the field, right? So, well, we don't have one charge, we have 3 charges. So what we have to do is 3QE equals 3 mg. Well, we do the obvious thing and cancel, and we should get that E equals mg over Q. Now, one thing we should always keep in mind is, what do we use for G? In questions where G is not given, always use G equals 9.8 meters per second. And what is Q? Q is the charge of a proton. This is another constant. It is plus 1.6 times 10 to the power of minus 19 coulombs. It's a constant. And the charge of an electron, so let me call this Q proton. Q electron is equal to the same thing, minus 1.6 times 10 to the power of minus 19 coulombs. Substituting in the equation, E equals, the mass is 1.67 times 10 to the minus 27 times 9.8 over 1.6 times 10 to the power of minus 19 coulombs, and we should get the E equals 1.02 times 10 to the power of minus 7 newtons per coulomb. That's the unit for the electric field. Why I chose 3 significant figures? Because in the given, the lowest number of significant figures is 3. We've answered one part, which is the magnitude. What's the direction? Well, given that the force is upwards, right? And since the charge is positive, well then, the electric field is upwards as well. But what if there were 3 electrons? Then the field would be downwards, because since the charge is negative, negative times upwards makes the direction of the field downwards. So the magnitude is this, and the direction is upwards. And one more thing to notice is that no matter how many protons they tell you, 3 protons, 4 protons, a million protons, no need to worry about the numbers because they cancel anyways. So in essence, what you should know is this formula, E equals mg over Q, for this type of question, where they're asking for the electric field that will balance the weight. Let's do number 9 now. A 45 grams insulating sphere carries a charge Q equals minus 40 microcoulombs and is suspended by a silk thread from a fixed point. An external electric field which is uniform and vertical downward is applied. Part A says, the applied electric field has a magnitude of 2 times 10 to the power of 3 Newton per coulomb. What is the tension in the thread? So now let's think about the free body diagram for a second. This here is the electric sphere. I've drawn the weight down and the tension up because it's suspended by the silk thread. Do you think I've drawn all the forces? No, right? Because it says there is an external electric field which is uniform and vertical downward. Now, as we all know, the electric force is equal to the charge times the electric field. Since the charge is negative, so the direction of the electric force is opposite the direction of the field. Since the field is downwards, then the force is upwards. So let me just draw the force like this. This is the electric force. Now what you have to do is find the tension. They've given us the electric field, so simply sigma Fy equals 0, which gives us tension plus the electric force equals the weight. So tension equals the weight minus the electric force, which is 0.045 times 9.8, because we always use 9.8 in questions where they don't give gravity equals 10, minus Q times E, again 0.045 times 0.045 times 9.8 minus the charge, which is minus 40 times 10 to the power of minus 6. Now, since we are dealing with the force electric, so we're not looking at the direction here, we're using the magnitude, we cancel the minus. So we just erase it, we remove it. So in this question, the only reason the minus was given to us was to make sure that we know the direction of the force electric, which is opposite the direction of the electric field. So when you're substituting, you substitute it as a positive number, times 2 times 10 to the power of 3, and when you're done solving, the tension should equal 0.361 newtons. Okay, let's continue with part B. Part B says the applied electric field holds the sphere in place above the point of suspension, and the tension in the thread is now 0.45 newtons. Find the magnitude of the electric field. So now a few things have changed. Now let's imagine this as the point of suspension. If the ball before was hanging like this, now it's hanging like this. It's held above the fixed point of suspension. So isn't the tension down now? So this way, now we know that the tension is downwards as well. Well, since two forces are down and we only have three forces, one of the forces has to be up, right? So the electric force is still up. Now let's use again sigma Fy equals 0. This time we are looking for the electric field. So that means we don't know the electric force. So Fe equals T plus W. So we have the T, which is 0.45. We have the weight 0.045 times 9.8, and we should get the electric force equal to 0.891 newtons. Is this the answer? It's not. We're looking for the electric field. Now the electric field, if force E, the electric force, is equal to the electric field times the charge, then isn't the electric field equal to the force over the charge? It is, right? So 0.891, let me just draw a line here, over the charge is 40 times 10 to the power of minus 6. You may be wondering why I'm not using minus 40. The minus just shows us the direction. Since they're asking us for the magnitude, the signs are all positive. And once we solve, we should get 2.23 times 10 to the power of 4. And since the unit of the electric field is Newton per Coulomb, then you have to put Newton per Coulomb. And that's the magnitude of the electric field.